So, guys, we agree that it would be nice for a network to respect or have certain inductive biases, or basically respect what happens in the real world. If that is true, then the architecture that respects that is the one that we are going to talk about now. This architecture, as I said, was one of the most successful architectures and is one of the most successful architectures. It's not going anywhere. What it is this. It says that we can reason with neural networks the same way that, for example, the receptive fields in the cats, the cats do it. Right? So how do we do it? To explain that, we need two concepts. We need the concept of something called convolution. And you'll see why. If we understand convolution and we understand the inductive biases, we are done. It's a home run from there. So what is convolution? There is a more strict mathematical definition of convolution, but allow me to be deliberately sloppy to convey the intuition of convolution. Imagine that there is a picture. It has a mountain, it has a sunrise, there are birds flying in the sky, and this. Are we together? And suppose I gave you this question that, hey, are there birds? We might as well grow a tree also, right? No scene is complete without a few tree for kids' images. I'm sure all of us have drawn this picture in our childhood, right? So are there birds in the sky? How would you answer? So imagine that you can't read it. You can't see it but if there are, let's say that you have something, a detector, a stencil. You know what a stencil is? It has a cutout. Right? And it basically says, so imagine this is black and white picture or something like that. I take the stencil and I slide it all over the image with one requirement. Is there any place in the image such that inside is all white? And I should have made this thing in black and white, and tree also in black and white, but okay. Inside is all white, outside is all black. If I find such a spot, what will it mean to? I have just found a bird in the sky, isn't it? I just discovered a bird. So a stencil. That is the intuition of a filter, of a convolution filter. The stencil is also, do you realize that it's a filter? Because it ignores everything else except your bird. Make sense? Right? That is the core intuition. And so the way this computer vision field evolved is you don't look for birds because there are infinitely many things. People would look for smaller things like edges, horizontal edges, vertical edges, and so forth. And if they would say, I found something interesting in the image. Right? And using that, they would try to figure out what this image is all about. Let me take you through that journey. And remember, at this moment, we are not talking really neural net. We are talking literally the concept of convolution, which predates this convolution. What it says is that this. See, if I have a function, fx, this intuition of a stencil, I'm going to make it more mathematical. Right? Suppose I have a function and I give you a magnifying glass, right? And the magnifying glass, if the more you magnify the image, the less of it you'll see, isn't it? right? So suppose, or maybe you are, imagine that you're a little ant and you can only see here. Let me use this color. You could see only this part of the image. And I ask you, what is the value of the function here? Right? Or another way to put it is, suppose I make it into a bounding box. This is delta x, right? You would agree that the area for the same delta x, the area, what happens if I do fx delta x? So now delta x is a function. Actually, let me call it gx. We come to gx. Okay. Look at it. Suppose I give you a lens that could only look at this, and I ask you, what is fx? There is no way you can tell that fx keeps changing. All you can see is a local view of the function, isn't it? And you would say fx is whatever, roughly speaking, this is. This is at, let me just call this x naught, actually. That would be a better way of putting it. Fx naught. You would just report back fx naught, isn't it? Now, this little view of the function, we can think of it like this. We can say that, imagine that you have another function, g of x, right? G of x is like this. X-axis and y-axis. G of y is equal to g of x. Right? And it is peaked at x naught. If I multiply fx with g of x at x naught, do you realize that that is what this function is doing? Look at this. That is what this function is doing, because everywhere else, so what is the value of g at x1? Your g function looks like this. Well, let me take a color. Right? This is your g function, right? So let me redraw this or magnify this. This is your fx, right? Your g at x naught looks like this. Right? Or something, it need not even be this tall, but let us say that it looks like this. Now, this is fx. This is g of x, right? So tell me, at points, I'll just randomly take points x1 and x2. At x1, what is fx times gx? 0, isn't it? Because gx is 0. What is it at x2? But at x naught, let us say that gx happens to reach unit size, approximately. At x naught, you would say that this is equal to fx naught, isn't it? Because fx naught, gx naught is equal to just fx naught. Are we together? So what does this product function do? It samples or reads the value there, wherever you put that sample function, isn't it? Wherever the peak of the sample function is, gx, wherever you put gx, it will go and read the value of the function at that point, right? Or if I go on multiplying fx and gx, right? Suppose I do fx everywhere, like I did it at x1, x2, and g of x, you know that at almost all the places it will be 0, except at gx. So if I just sum integral is nothing but summation, right? Gx, and I'm using deliberately being sloppy, because mathematically it's a little bit different. You would say that this would just be fx naught, more or less, right? It would basically be fx naught, something like this. Right? So this kind of an operation, which probes, it's a probe, isn't it? It's a probe that is looking at the value of a function in a neighborhood, in a specific neighborhood. These operations, this is called a convolution. Mathematically. The only reason I'm explaining is people keep saying CNNs are fine, but I don't understand the math. What is this math? Do you see that it's a dead obvious math? Right? G is the probe. So the filter, and G is the convolutional filter. G, convolutional filter. Why is it a filter? Because it ignores the value everywhere else except around x naught. Isn't it? As far as it is concerned, the rest of the function might as well disappear. Right? Now, let us tie this to the idea of a stencil. Right? Let me do that and show you a little bit of a magic. So far, so good, guys. Are you together with me? Do you understand what convolution is? Convolution is a product of two functions. Now, just to whet your recollection, an image is lots and lots of numbers, isn't it? Lots and lots of numbers. Pixels. Let's take black and white image. So they are just, each of these pixels has a value, right? Let us consider the value of, so let me take, now this is a discrete situation because pixels are discrete. Ith row and jth column. Ith row, every pixel, the coordinates of a pixel is ith row, jth column. Makes sense, right? So at that, whatever the value is, let us call it the fxij, pixel value at that point, at that location, right? Or just fij. It doesn't matter, right? Whatever number it is. It might be, 0, it might be 1, it might be something in between, shades of gray, some shade of gray. Imagine black and white. Now, here is something strange we'll do. We will create ourselves a stencil. Let me use a different color for a stencil. What would be good? Blue might have this. Imagine I'll deliberately take a 3 by 3 stencil. And let me do something. Put a big number in them. And put some numbers in here. And you'll see why I'm playing this game. Right. Then, let us say that this picture actually is a picture of a, let us say it is a picture of a 4. So let me take a big color. 4 magnified. Just bear with me. And here we go. Would you agree that this is a fairly respectable looking 4? So this is a, now what it means is if the picture only has this 4 and nothing else, it means all the other pixel squares are 0. And inside the 4 is 1. Let's take a simplified situation. And what we will do is we will take this stencil, this 3 by 3 stencil, and start at the top right hand of the image. And we'll keep sliding it, scanning, right? So in the beginning, let us say that the machine is here. They are all 0. So this is your g of x, g. Right? So what happens at the top left, the function is every element there for the time being. And if you look at the situation, in this situation, let's say A, at A, all the Fij are equal to 0, right? Or Fx is equal to 0. And so Fx, g of x will be equal to, and integral becomes summation. So in the discrete case, remember, integrals become sums, right? All of the ij, gij. Because -1 you multiply with the top left, what do you get if you put the stencil there? So whatever number, you have a number from the image and a number from the stencil, right? Multiply the two together. So -1 times 0 is 0. Well, and so forth. And even 8 times 0 is 0. So what does the filter add up to? 0, right? So you create a little table and you say, okay, in the beginning, 0. Now you move the filter a little bit to the right, right? You move it to this location. Sorry. I lost my writing part. Let me know if you can see this purple little box. Now tell me, what do these numbers multiply up to in this situation? I just slid it a little bit. The only thing non-zero is this white bottom corner. So this will take on value -1, isn't it? Then I slide it a little bit more, and let's see what happens. I slide it. Let me use another color. I slide it to this. Tell me, guys, if you multiply all of it, what does it become? -2. Something strange is happening, isn't it? Something interesting is happening. Right? And I slide it one little bit more. And now let's see what happens. I make it, let me use another color. Let's take orange. So now I take it here. And now what happens? -3. And then I slide it over to this. What does it happen? -2, -1, 0. After a while, zeros. It will all be zeros. And now let us do one thing. Somewhere down the line, let's bring this filter. So second row, we can fill the second row also. Tell me, guys, if I do this, what do I get in the beginning? 0. Now I displace it a little bit. What do I get? -2. And I displace it one more step. So now it is here. Let me use another color. Suppose I display it here. Of course, we got -2. Am I making 3 boxes? 3 boxes. Okay. What is happening now? There are 4. So 8 -3. 5. Something interesting is up, isn't it? Right? This has taken on a big value. In fact, the first positive value it took on. Right? And I bring it all the way back into the fold. What happens? Let's say it becomes this green box. What is it now? 8 -1, 2, 3, 4. 4. It will become 4, isn't it? And then I slide it once over, it will become, if I slide it, 1. So just follow along with me, guys. This is once in your life, you have to do this completely on your own. So now it is, let me color this heavily. Tell me, what does this filter say now? 8 in the center and 3 minus 3, 5. Right? So 5. Right? And I move it beyond, I move it to this side again to, let's say, you can keep playing this game, guys. The point that you'll see the point that I'm making. Suppose I make this. Now what happens? Most of it is blank. It's -1, -2, right? And the rest of it is all zeros.
Awesome.
Yeah. Oh, it should be 3. Okay, so 3. And is this 5 correct? Something odd about this 5. Yeah, this is correct, right? It's an edge. So now observe, suppose I bring it 1 step below, and this will be fun. Now the fun begins. Let me take this filter, 1, 2, 3. This is, of course, 0. So I start with 0. Now move it across a little bit. It becomes -3. And see the fun that happens. I move it one more place apart. 8 minus 5, right? It becomes +3. It suddenly jumps. Right? And then I move it one more place forward. And the whole thing is now, what happens now? It becomes 0. So roughly speaking, you can convince yourself that whenever you're completely inside the white, it's 0. And completely outside the white, outside the digit is also 0. But some drama happens only when you have it somewhere here, right? So can I just make a somewhat irrelevant story? Right? So apparently in Indian mythology, there's a story that one of the gods, I believe it's Shiva, once gave a boon to some demon who was really worshipping, praying really hard, or doing a lot of penances. That, okay, ask what you want. He says, I should not die. And apparently the god said, so be it. So he goes. Then he creates a lot of mischief. And all the other gods are very worried. What have you done? So he cannot be killed. So then he modifies it, puts a rider on it. He says, you cannot be killed inside the house, you cannot be killed outside the house. Correct me, guys, if I'm getting the story wrong. Right? And so then he is killed on the veranda. Right, or something like that. So it's somewhat like that. Do you notice that this filter is no use outside the 4, is no use inside the 4, but lights up on the edge. Right. So what is this filter doing? This filter is an edge detector. Throughout your picture, it will detect all the edges. Would you agree, guys? No? And if you light up the values, you will notice that the value, it will take on value. You will see that the places that are lit up are all like this. So isn't it? It is the edges where things happen. It is an edge detector. Likewise, convince yourself that if I made another stencil, another filter like this, -1, -1, -1, 0, 0, 0, 1, 1, 1. It would detect horizontal lines. Rotate it, it would detect vertical lines. So people realize that by doing convolution, what is mathematically convolution, which simply means take the stencil and go all over the picture. You could detect interesting properties in the picture. Where is the edge? Where is the horizontal edge? Where's the vertical edge? Things like that, isn't it? Right? You can, for example, I invite you to find a filter for X, right? You can do that. So you can do all sorts of things. And in computer vision, oh my God, like my textbook from the 1990s is still on my bookshelf. If you look at it, you'll see that many things are described there. but neural networks is a tiny little thing somewhere, right? It's hardly mentioned, right? So these filters are there. So these filters, people began to say what they would do is they would detect features. They would find interesting features, or people call it the key points in the image. And by knowing the location of the key points, key features, they would then predict what it is. So they would try to predict that it's the letter 4. It's the digit 4. Sorry. Is it making sense, guys? They would do that. That's what it was. So then people had different collections of these filters. People would say, oh, my stencil collection, or more mathematically, my filter collection is better than your collection, right? And they would go about writing papers on it, right? Showing that this filter collection is superior to the previous filter collection and so forth. That's how research makes progress. Now, where does neural network come in? It came out with an interesting idea. It basically said, and pay attention to what it is saying. It's saying that, see, guys, we are cooking up filters by hand, isn't it? This convolution filters, we are cooking it up by hand. But what if we did this? Because we are trying to detect features that we think matter. What if we did this? What if we said, let the machine discover the best filters to do a job? Right? So it sounds like a preposterous idea. It says, suppose I have my collection of filters, let's say 20 filters, whatever. So now I had my 20 good filters that I've really attached to because I believe they get my work done. And here comes a guy and he says, let's do one thing. Forget your filters and have your filters, but what do you fill it up with? You don't know. Just fill them up with random numbers, right? Random small numbers. No, just fill them up with random numbers, weights. These are called weights in the neural network language. So you have filter 1 all the way to, let's say, filter, pick your number, 20 filters, 16 filters, whatever, and fill them up with random numbers. So now you would say, what in the world are these things going to find? They're not going to find anything at all, isn't it? They say, no matter what, do this now. Take the image of a cat and feed it into these filters. You will get something, right? You'll get from all of these filters, you'll keep getting something. At the end of it, concatenate them and somehow convert it into a long vector, somehow, a long final vector. And that vector, you can always pass it to a logistic function, classifier. At the end, put a simple classifier network. We all know how to draw that, right? And just ask cat or dog. So let us say that you did give it a cat. Suppose Y was cat. The answer was cat. And X is, of course, the cat image. The answer is cat. And here, the only thing you care about is what is the Y hat is probability of a cat given X. This is your Y hat. So suppose, now tell me one thing. If the probability is high, is the machine doing well, right? Of a cat is doing well. But if the probability is low, the machine is not doing well. Now, whether those filters are random or not, if you consistently get good numbers out of it, nobody has told you that those filters have random numbers. But suppose magically you throw some pixie dust and this machine starts producing good predictions. Like for cat, it says cat. For dog, it says high probability for dogs. If it could do that, you would be not able, would you agree that those filters must be working? Otherwise, there's no way this could work. This can happen, isn't it? And that is the core idea. Can we discover somehow? So our whole question is, how do those filters sort of learn to find, the best feature in the images? right? We will come to that because we know that theory, backpropagation, gradient descent, and so on and so forth. It turns out that neural networks has that theory for you. And so all you do is in the beginning, you feed it, the weights are random, and it will say probability of cat is like 0.5 or something like that, some random number. Wrong. All you need to do, so what happens is y hat is, see, the entire neural network, as far as you are concerned, it is just a function. Right? Remember, a neural network at the end of the day is a function. No, it's a forward function. Right? So you do of the function. Y hat is what? It is the probability. Higher the probability, the better it is. The lower the probability, the worse it is. Now, how do you convert a probability into good and bad? What you can do is, look at this. Suppose the probability was 1. The prediction was 1. Has it made a mistake? No, right? Mistakes are called losses. So you want loss to be 0 when probability of a cat is 1. Isn't it? Suppose the machine predicts. Now, how do you convert a 1 to a 0? One easy way is that you can, there are many ways, but let's take the log of p, right? And suppose it says probability of a cat is 0.000001, very close to 0. It's made a huge mistake. We need to really punish it. This is 10 to the minus 1, 2, 3, 4, 5, 6. Big blunder. Now, how do we convert it to a big number? This tiny little fraction. How do we convert it into a big number? Take the negative log. So if you take the log of it, it will become -6, not good. Right? So you take the negative log and then it becomes big number, 6. Do you see that? So that is called negative log likelihood, this loss. So for classification, this is the most common loss function used. You see that? All I need to do is, I need to just do the forward pass, figure out the loss. But if I have the loss, what do I do with the loss? Oh, I can do gradient descent and backprop. I can change the filters a little bit so that it makes less mistakes the next time. Isn't it? Next time I pass it, it will make less mistakes. It learns from that. No, you got it wrong. Change your weights a little bit. But let the machine discover the best weights. And you keep on doing it over and over again with thousands of images and lots of epochs, lots of iterations. And so what will happen is all of these filter weights, they will do two things. They'll become really good filters. They will, first of all, coordinate with each other. They won't copy each other's because then they become redundant. Yeah. They will all start looking for something interesting in the image that helps them tell a cat apart from a dog. Right? They will optimize themselves for this task. And so you will end up with a set of filters that is really optimized for this task. Right? Now, what happens in between are the details of the CNN details. And I've mostly taught you that. A little bit remains, but you realize what an interesting idea it is. You take the filters and convolution, which have existed in computer vision, but you're saying, what if it could be learned through a neural network? Right? That is it. That is it. So let us recap what you do. Now, observe something very interesting. That edge is an edge. Wherever it is in an image, it will detect it. If the edge moves from here to here in the representation, in the output, also the same numbers will move this side, isn't it? So you have translation equivariance, right? Isn't it? Right off the bat, you have translation equivariance. Now let's look at other features. What else? So how are these networks created? What you do is, when you do the convolution, you apply the filter across the input pixels. So that is called a convolution operation, right? So when you multiply, let's say -1, -1, -1, 8, 0, -1, -1, -1. So with whatever value, you product Fij times the Gij, this is G, and you sum over all the Ij, the 3 by 3 Ijs, that the value that you get is the output, isn't it? Output at that location, right? At that location, at the top left location, at that location. So you take this output, but you don't just take this output, because remember, neural networks, the way they learn nonlinear features is through what? This is a linear operation. Yeah, you need to apply an activation function. So what you do is, and let's just say that some activation function, we'll just apply tanh. At some point, it used to be very popular. Nah, f dot g, you would do tanh of it, right? I'll put the summation here, right? You would activate it, and then you would get the result. Now, that is good. But then, so if you do this, you will get an output table of values coming from the image. But if you're careful, you will notice that your output is actually smaller. Why? Because if you think about it, this 3 by 3 filter, it cannot go beyond this image, right? It has to stop, right? So because it has a certain fatness, so it's like, suppose I walk all the way to the wall. You think the back of my head is going to touch the wall? No, because my significant belly will come in the way, right? So there is a certain loss here, padding loss here, right? So the image that I'll get will be smaller image, right? It gets smaller. So what does that mean? The next, suppose I were to do this, and let's do one more thing. It is called the padding operation. Right after this, what people do is, and you'll understand why padding is done. You take a 2 by 2, like let's say in this, just apply in the output. So the output is huge. It's huge. Just take a 2 by 2, right? Another kind of filter is called the padding filter. So first you applied your real fancy filters. Now you apply a simple padding filter. What this kind of padding filter does is, these are called padding operations. Not padding, pooling operations, sorry. These are called pooling filters. Pooling. They don't use the word filters, but they are filters. What you do is, suppose you take a window like this. And here you have certain values that have popped out. You have 3 choices. You can either pick the min, max, or average. Right? So, and I'll give you because we are now you're getting due for your lunch. So I'll summarize it quickly. What it does is 2 things you get from pooling. A certain insensitivity to local perturbations, right? So for example, a cat, if it just moves just 1 pixel away, you don't want the representation to change that much, right? If it moves from here to there, then the representation also should move there. But just a little bit of a change, it should be insensitive to some insensitivity to small perturbations. So pooling gives you, especially the averaging kind, it gives you insensitivity. Likewise, the min and max give you. See, if I pick the min here, suppose therefore this is there, and whatever value is here, let us say that the min was here. All right. And I move this pooling filter one place to the right. Now, all that will happen is my min will still be the min, isn't it? Do you realize that this padding, if it just picks up the min, moving it just a little bit. So in other words, locally, the values don't change, isn't it? And the same thing applies for max and for average, right? More or less. So what they do is they bring in a certain amount of insensitivity to tiny changes. perturbations. The other thing that they do is if you take the min or the max, right, it sort of slightly amplifies the value. Like if it is white, you're looking for white on a dark background, it just becomes a little bit easier to pick it out, isn't it? It will say, oh, white, 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 white. I saw white, right, in this neighborhood. It will keep on saying that.
We started with the padding, so that the concept is the pooling actually.
Yeah, sorry. I used the word padding. I should have used the word pooling. Pooling.
No padding.
No padding. I misspoke. Pooling. So, guys, there are two uses of filters, I told you. With a filter, which in my mind is a stencil, right? With filters, you can do two operations: convolute and pool. Right? First, convolute. Having convoluted, also activate, then pool. Convolute, activate, pool. Activation function, right? The convolution operation, and then apply the pooling operation. The doing of all three together makes one convolutional layer in CNN, convolutional neural network. When you have these three things all done to the input image, you have done one layer of convolution. Are we together? Go ahead. Pooling is just another kind of filter. So suppose I have an image. See, I convoluted. So suppose there was a cat. I convoluted and activated. So when I convolate, I'll get some numbers. This is F cross G, right? And I have my filter G. G. I did F cross G is the output of the convolution. But that thing, I activate tan H, right? And then I get yet another table of numbers, right? And then I apply pooling. Pool. And pooling will again shrink the size a little bit, right? Because it has a certain width.
It's kind of filter on filter.
Yeah, it is just another filter. And it's a simpler filter in the sense that you don't multiply, convolute. You just pick the biggest or the smallest or the average.
There are two filters now.
And these three operations together makes one layer of a CNN. Now comes the idea, why do I do that? Why pool? Why do all of this convolution? See, together what happens is you realize that the output of this pooling would be smaller. The image has shrunk, isn't it? It's no more 100 by 100, smaller. And now, if I still go over a 3 by 3 filter or whatever, do you realize what is happening? I am zooming out, right? So things that were a little bit, not just the eye of the, inside the eye of the cat, but the other part of the eye has now come within my receptive field of this filter, isn't it? Because after the pooling, the image has shrunk, means information has come proximal, more proximal to each other. So if I still use my 3 by 3 filter, you usually use odd numbers, 3 by 3, 5 by 5. If I still use it within the receptive field of the filter, convolution filter, now more feature is there. Why is that useful? So what happens is, so I'll just write layer by layer, layer 1. And remember, these are CNN layers, conv layer, another conv layer. It is gradually zooming out. It gives you one thing that we were searching for. Do you think it will help us with the hierarchy of features? Right. So now let's go through the checklist. Did we get this? No. The insensitivity to perturbations? Did we get translation equivariance? The edge is an edge. If you move your edge, the representation output edge, the location will change. By going from one layer to the next, I am benefiting from the hierarchy of features. And locality of structure is there. Of course, I'm benefiting from that. Yeah. And so what you create is a network that has as inductive bias properties of the real world. Whenever you create a neural network that has such inductive biases from the real world, they generally outperform, for example, a vanilla MLP feed-forward network, which has no inductive bias at all, right? And it is actually a lab. I'll have my teaching staff post that lab. You can see comparison, doing it with feed-forward network and doing it with CNN.
We did it yesterday.
Well, that's true. If you're in the intro to AI course, you have just done it. Yes, that's true. Yes. Yeah. So for you, it'll be a repeat. That's true. For those of you who else is there in that class intro? Okay, many of you are there. Yeah. So you have actually seen this in real life. Now you know why it happens. So for you, the repeat will be when I explain the rest of the stuff to you guys next time. Maybe I'll skip it. No,
Show it. I want to see it again.
Yeah. So go ahead.
We haven't got cooling in the other.
Yeah, we haven't gone there. We haven't. So guys, now Jeffrey Hinton and these luminaries, they called it representation learning. See, what is happening is layer by layer by layer. And by the way, what you do is each filter will discover its own feature map, isn't it? The output of each filter, each of these G's will be its own output. This is called a feature map. Output is a word people use for the output. So you realize that suppose I have 20 filters, G1 to G20, I'll discover 20 feature maps. The way you think about it in this field is you say that these feature maps that I'm getting, they are representations of the original image, but you are getting to higher order representations. Remember, it's like, you look at the eye, then you pixels, that black thing, then you zoom out, oh, that black is the black circle of the eye, the iris, right? Then you zoom out a little bit, you say, oh, it was the eye, that the sphere was the eye, right? And you zoom out, okay, eyes belong to what? Begins to look like a face of a cat, right? So that zooming out and the fact that you're creating all of these feature maps, stage by stage, now what are you doing? So that every successive layer is being fed the input from the previous layer. So it is not learning from the original image, isn't it? Like layer 2 has no access to the original image. It has only access to information coming through layer 1, right? So it is learning from representation coming out of layer 1. That's all it can know. And hopefully, if this network is doing a good job, it has to take this input representation and create a higher order representation, right? And that's why this thing, deep neural networks, they are often said that what they do is representation learning. That's actually a better way of thinking about it, that it's systematic or hierarchical representation learning, isn't it? You literally see that working in CNNs, right? Yeah, go ahead.
So the cooling is applied.
Yeah.
After the filter is applied to the entire image.
After the convolution filter and the activation. So remember, convolute, activate, boom.
That's all the entire, all the pixels.
All the pixels, yeah. Slide it all over.
Sorry.
To create the feature map. So what happens is, let's look at it. For one layer, for every filter GI in the layer, let me use the word GA in the layer, input goes through convolute that creates its own feature map. It creates a feature map of convoluted map. That is fed into activate. Activate, let me just put a box here. Activate, say tannage. That will produce its own feature map. Again, the feature map changes now because it's activated values. And finally, this goes through pooling and it goes through pooling, and what comes out is a third feature map, and it is still GI, and now feature map I, right? And suppose you have 20 filters, how many feature maps will you end up with? 20. So the way these networks are designed is, and people found beneficial is, if you want to learn higher and higher abstractions, as you go down in successive layers, you increase the number of filters. Are we together? You may go from, let's say, 8 filters to 16 filters to 32 filters to 64 filters to 128 filters. But the feature map size keeps shrinking. Are we together? Unless you use techniques like padding, etc. Some of those details I usually do in a more specific or detailed coverage of convolutions, but they are not. We don't need it for this course. Yeah.
The pooling.
Yeah.
Let's take the example of the previous work we did, the manual calculation.
Yeah.
Is the pooling filter the same size as the
No. Pooling are typically 2 by 2. Pooling done typically. And you notice we are using even numbers.
For pooling.
Yeah. But for convolutions, you typically take odd numbers. That's another way to recognize whether you're convoluting. Nice. And pooling is usually min, max, or average. So there's a wealth of literature. You can see that there are a couple of things I skipped. I didn't tell you about padding. So you can keep the image size still fixed by padding it all around with empty pixels before you. So it gives you space to go.
Edge detection, the images at the edge, or
Yeah, that's right. If there's something at the very edge to capture that. So people do padding, and also to make sure their feature map doesn't shrink. They can also do strides. They say that, moving 1 pixel at a time is too slow. Maybe we'll jump 2 pixels at a time.
dialing.
Nice, jumping around a little bit. So that is called the striding, right? So you can do padding, striding, but the core ideas remain the same, right? It's just minor variations of it. So guys, you just learned convolutional neural nets. The first convolutional neural net was, one of the first successful ones was LeNet, which was used by the US Postal Service. See, when you do handwriting recognition, when you write a handwriting, mails used to be written, if you remember, there used to be these ancient devices called pens and pencils, right? And you would write on paper. So I'm kidding. So when you did that, everybody's handwriting is different. Somebody writes a 4 like this. Somebody writes a 4 like this. Somebody writes a 4 like this, right? Somebody writes a 4 like this. And then this 4 begins to look suspiciously like a 9 or something like that, isn't it? And so everybody's handwriting is different. So the National Institute of Standards and Technology, a US government body that tries to standardize everything, they created a data set to compare all the models to see which is the best, right? So NIST, National Institute of Science and Technology, is a pretty respected body in US. And they created a data set of digits, handwritten digits, right? They used to be 28 cross 28 pixels, very tiny because machines in those days didn't have much computational power. And their grand challenge was, say there are about 60K images, out of which 50 is the training, 10K is the validation set. So the idea was, what kind of accuracy are you getting? So the numbers were, human beings are between 91 and 93%. The best of us, the best of postmen, get it to about 93. The algorithms in those days used to do pretty poorly. They would be around 73 or so, right? In fact, before this convolutions came up, the state-of-the-art algorithms were support vector machines, right? And in fact, even today, in fact, if you look at the medical domain, you will realize that in the image, MRI image, X-ray images, etc., there are only two algorithms that dominate: support vector machines and neural networks, right? Everywhere. And within neural networks, it is CNNs and transformers. So the field that you're talking about. So we won't do computer vision with SVM because we have limited time. But so you had 28 by 28 pixel and everybody was supposed to. So what happened is when this LeanNet came out, it had amazingly good accuracy, so good accuracy in the higher that fairly good accuracy that people thought that let's adopt it. Government actually started adopting because they found that, it expedites things. Today, using CNN, so now using the latest CNN architectures, can you guess what the latest CNN architectures give you as accuracy? On the M. So there is a M also before it. M is the modified. They had to fix the data sets a little bit. Modifiedness. What's the accuracy today?
Maybe 90%.
In fact, the only errors that exist are things where people have just left like this. Can you tell what digit it is? It is actually unfair. So in the MNIST, there are these digits that no human being can make head and tail out of. But it has been labeled as a 2 or something like that, right? In fact, anything that's a legitimate digit, the CNNs get it perfectly right. What is the real world impact of this? Remember, there used to be a time in the 90s when you could, when your, let's say, your dad or your mom calls up, you haven't written to me in a month. And you realize, oops, no, I wrote to you every week. I don't know where the letters are going. The young kids would say, right? Today, you can't make that excuse. Why? Because letters don't disappear. Right? And a large part of it, there's no misrouting of letters. They don't go to odd places and then there is no dead letters. I mean, there are dead letter centers, but the volume reaching there is close to zero. The reason is when you put your mail into the mailbox, the mailman just carries it to the post office and dumps it into a machine. Into the machine are sitting the CNNs, these neural networks. Automatically, they recognize what's written on the envelope, handwritten on the envelope. And if you look at any letter at the bottom, do you see these little black squiggly marks? That is the digitized version of the address. Once that is there, it gets through this automated sorters that sort it, route it, take it to wherever. And the next human intervention generally happens when in a box, the typical postman's box, is handed to a postman saying, this is for your neighborhood. Right? And that fellow comes and distributes the letter. The rest of it is fully automated, and it's only possible because of the CNNs. Because of these computer vision technologies, this sort of neural networks, today, and not CNN, but the next one we'll talk about transformers and advances. As you know, the big breakthrough of this year was that just a few months ago, Google came out that the AI using transformers and mix of CNNs and transformers and so forth, their diagnostic accuracy exceeds that of the best radiologists. Best radiologists. Right? In fact, by looking at the optodome, for example, a few years ago, there was a big discovery. Looking at, people have been looking into your eyes, right? Every time you go to a eye doctor, they'll take a picture of your eye and then they'll tell you that, oh, look at this and that and so forth. But they're only talking about the eyes. AI looking at the eye can tell whether you have diabetes. Are you likely to have diabetes in the near future? Do you have heart disease? How much of heart disease you have? It's all written there. Nobody expected it. Breast cancer, right? And all of these things. So the state of the art of AI and vision tasks has reached the level. And now we are going to talk about it as we move forward. You will notice that not only can it find those things as a classifier and say, yes, this is malignant or something. This has this probability of having this. It can write a very detailed interpretation, the medical note. So there's something called And the way the consult happens is, and Sukhpal is a physician, so he'll correct me. There's a format called SOAP, right? Sort of subjective. The patient says, oh, I have this and I have that. And by the way, the weather was nice outside, right? And doctor filters out most of these and makes some objective scientific notes, right? Subjective, objective. Then you have an assessment. What exactly do these things mean, right? So those are often at the end of it, they lead to some form of ICD codes and things like that, and some CPT code, some procedure to be done, right? Plan, what do we do, right? Your plans, CPT code. So those are the things. The amazing thing now is with AI, the state of the art AI, and especially, and that is why I was eager to bring you into this territory. Many of you are saying, why are you moving away from RAG so soon? It's because we have many interesting things to come to. You will be learning how a machine looks at an image and comes up not with a detailed explanation of what it is seeing in human language. And those notes are so good that here's a situation. I am told, I don't know how true, Sukhpal, you can correct me, that almost all young physicians now, whenever they get this thing, the first thing they do is they reach out onto the web and they're consulting some AI to help them diagnose what is going on, right? And the Medical Association tried to stop that. They tried to ban people from using these
Even for X-ray,
language models.
even for X-rays,
Come again?
even for X-ray image also.
Yes, yes. And so what is happening now is the thing is moving so fast that AMA, the American Medical Association, finally realized that you can't stop people. So let's teach them how to use these tools correctly. Right? So because you can't completely trust it, they do make mistakes. Right? And they miss things.
All the
And so,
young residents, they would use.
yeah, all the young residents are now using that, right? So can you see the inversion that has taken place, right? And so this is the topic I'm taking you guys into. Hopefully, by the time this bootcamp finishes, wouldn't you like to reach a level at which your code is doing things like this? Right?
All the patients were complaining there is no eye contact.
Yeah, because people are just looking at the image.
So Kaiser have trial going on. Yeah, all the big ones.
Right. So anyway, guys, and now what we are finding is that these machines, these visual language understanding machines, or computer vision machines, they are able to diagnose or they are able to detect forms of cancer years before any diagnostician would. Right? Just think about it. The earlier you detect a cancer, the more likely you'll sail your way through it. Right? See, cancer is what is called immunal escape. As you know, and I'm told, so correct me, that see, in our body, right, cancer cells keep popping up, runaway cells. But our immune system is smart at it. It's an army on the watch out for it, and it goes and kills it. There are phagocytes that will go eat it up, right? But cancer happens when there is an immunal escape. I mean, in other words, those cancer cells are not detected by our immune system as the enemies. Right? Then they proliferate. And the earlier you catch it, the less destructive is the procedure to get you out of it. And today, diagnostic tools are emerging as of 2023-24, which actually discover cancer or precursors to it way, way before human physicians can. Right? So just giving you a flavor of it. So anyway, with those words, let's go have our lunch. I will not do CNNs. I will do a little bit more of CNNs, and then we'll go into visual transforms. Let me stop the recording now.
And then don't forget to mention that breast cancer, 5-year lead time.
Yes. Okay. Like Sukhpal. By the way, Sukhpal here is a physician.
Doctor.
Yes.
I'm a
he's
doctor, but I am into informatics. And I work for Kaiser.
Yeah.
So I have a friend who is right now dying from breast cancer.
Okay.
And machine learning can detect that same breast cancer 5 years early. So every female should do this.
That's right.
Radiologists, they are 5 years behind.
Yeah. Yeah, thanks. Thanks for sharing that. And especially, guys, see, it's a bad thing to have cancer, but somebody once told me that if it is a given that you have to have cancer, the luckiest thing that can happen is you get breast cancer and it is discovered in the very, very early stage, because then it's mostly curable.
Yeah.
So. All right, guys, so we'll take a lunch